A few minutes after the universe was born, it started cooking. Not metaphorically, not spiritually, not like your auntie cooking when she gossips at weddings. I mean literally. The newborn cosmos became the hottest kitchen in history, an expanding fireball forging the first chemical elements out of pure chaos in physics. Hydrogen, helium, a little bit of lithium. And for decades, physicists thought they had the recipe nailed. But then they checked the pantry, and lithium was missing. Not all of it, just enough of it to make cosmologists stare into the void, like a man who followed the IKEA instructions perfectly and still ended up with 4 screws and an existential crisis. This is the story of the cosmological lithium problem, one of the strangest unresolved mysteries in modern astrophysics. Because according to the best equations we have, the universe should contain about 3 to 4 times more primordial lithium than we actually observe in ancient stars. So where did it go? Did the universe miscalculate? Did stars destroy the evidence? Did new physics sneak into the first minutes of time like a cosmic burglar? Tonight, we follow the lithium trail all the way back to the beginning. The first 3 minutes of everything. Let's begin where every good mystery begins, at the scene of the crime. Roughly the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to fuse the lightest elements. This era is called Big Bang nucleosynthesis, or BBN if you want to sound like someone who owns at least 2 whiteboards. This process made mostly hydrogen, helium, traces of deuterium, a little helium-3, and tiny amounts of lithium-7 and beryllium-7, with much of the lithium effectively arriving through beryllium that later decays into lithium. Now, here is what makes this so beautiful. This is not one of those maybe, perhaps, vibes-based cosmology stories. The predictions come from a theory with very little wiggle room. Once the cosmic baryon density is fixed by the cosmic microwave background, Big Bang nucleosynthesis gives you sharp expectations for how much of these light elements should exist. And for most of them, it works astonishingly well. Deuterium? Good. Helium? Pretty good. Lithium? Lithium walked off set and refused to honor the script. The cosmic receipt doesn't match the bill. This is the heart of the problem. Standard Big Bang nucleosynthesis, combined with modern cosmology, predicts a primordial lithium abundance that is roughly 3 to 4 times higher than what astronomers infer from the atmospheres of very old, metal-poor stars. That is not a rounding error. That is not, oops, forgot a decimal. That is a giant cosmic mismatch. Think of it like this. Imagine checking your bank account and discovering that, according to official records, you should have $4,000, but when you open the app, you see $1,200. And now imagine the bank says, "No worries, the math is excellent," and you say, "That would be more comforting if the money also existed." That's the lithium problem. The equations say the early universe should have made more lithium than we can find in the oldest stars that ought to preserve that ancient chemical record. So either our measurements of those ancient stars are fooling us, the stars changed the lithium after they formed, the nuclear physics is incomplete, or the early universe did something our standard model does not include. And that's where the rabbit hole opens. The ancient stars that should remember everything. Astronomers went hunting for the oldest chemical witnesses they could find, metal-poor halo stars. These are ancient stars with very low amounts of heavier elements, meaning they formed early, before generations of stars had time to enrich the universe with cosmic leftovers. That makes them prime candidates for preserving primordial element abundances. Back in the 1980s, astronomers Francois and Monique Spite found something remarkable. Across many of these old stars, the lithium abundance seemed almost flat, a near-constant value, now called the Spite Plateau. At first, this looked like victory, A plateau, a clean signal. The universe had signed its name. But then came the bad news. The plateau value was too low. Instead of matching the lithium abundance predicted by Big Bang theory, the stars seemed stuck at a lower value, roughly around A of lithium equals 2.0 to 2.3, while the predicted primordial value sits much higher, near A of lithium equals 2.7 in the classic framing. And just when astronomers thought the story was consistent but low, things got worse. At even lower metallicities, the plateau begins to fall apart in what researchers call a meltdown. The lithium abundance becomes scattered, erratic, and shockingly depleted. So the stars that were supposed to be clean fossils started looking more like crime scenes after a hurricane. Suspect number 1. The stars ate it. The first suspect is the obvious one. Maybe the lithium was there and the stars destroyed it or buried it. This idea has gained serious traction. A 2024 review summarized growing evidence that stars may lower their surface lithium through internal transport processes, especially atomic diffusion and related mixing mechanisms. In plain English, the lithium may sink below the visible surface or get moved into hotter layers where it is destroyed. And that matters because astronomers usually measure the lithium in a star's atmosphere, not by slicing it open like a cosmic avocado. If stellar physics has been quietly shuffling lithium out of sight, then the old stars might not be faithful record keepers after all. This is huge because it means the Big Bang may not be wrong. The stars may just be bad historians. Some recent work even argues that once you account for stellar evolution, chemical evolution, and the role of the first stars, population 3 stars, the universe's original overachievers, the discrepancy may shrink dramatically or even disappear in certain models. But, because nature never misses a chance to stay dramatic, this is still debated. Not everyone agrees that stellar depletion alone solves everything. The data at the lowest metallicities remain messy, and different stars seem to tell different parts of the story. So the stars are suspicious, but not yet convicted. Suspect number 2. The nuclear recipe is off. The next suspect lives in the first 3 minutes of cosmic chemistry itself. Maybe the nuclear reaction rates used in Big Bang nucleosynthesis are slightly off. Remember, primordial lithium-7 is closely tied to the production of beryllium-7, which later converts into lithium. So if you alter the pathways that create or destroy beryllium, you can change the final lithium outcome. That has inspired years of work on reaction cross-sections, weak transitions, radiative channels, and every little nuclear loophole physicists could kick open with a crowbar. The problem? Most attempted fixes run into a nasty side effect. They tend to mess up deuterium, one of Big Bang nucleosynthesis's big success stories. Several studies note that reducing lithium often pushes deuterium out of the observationally allowed range. In other words, you fix one leak and burst the pipe in the next room. That is why the lithium problem is so stubborn. The universe is over-constrained. You can't just change one thing and walk away whistling. The other light elements are watching. Suspect number 3. New physics hid in the baby universe. And now we reach the part of the story where theoretical physicists roll up their sleeves, crack their knuckles, and say, what if the early universe was weirder than we thought? This is where the lithium problem stops being merely a chemistry issue and starts flirting with new physics. Researchers have explored all kinds of possibilities: decaying massive particles, altered neutrino properties, extra dark components, modified expansion histories, entropy changes, non-standard Big Bang nucleosynthesis, even tweaks to the time-temperature relation in the early universe. The appeal is obvious. If the standard model of the infant universe slightly missed the plot, lithium could be the clue that gives it away.
But again, there's a catch. Most of these ideas are constrained by other observations. You can't invent a dramatic new early universe mechanism unless it also plays nicely with deuterium, helium, the cosmic microwave background, and the fact that the universe has spent 13.8 billion years refusing to collapse into embarrassment. So lithium sits there like a tiny chemical troll under the bridge, demanding payment from every cosmological theory that wants to pass. Plot twist. Maybe there was never missing lithium at all. Now here's the twist that makes this mystery so delicious. What if the phrase missing lithium is itself misleading? Maybe the lithium didn't vanish. Maybe the universe made it. Maybe it was there all along, but by the time the oldest stars formed, evolved, mixed, accreted, diffused, or got chemically tangled with the first generations of stars, the amount of lithium visible in their atmospheres no longer matched the primordial truth. In that framing, the problem is not where did all the lithium go? It's why did we assume old stars
Were perfect recorders of the beginning? That is a much more interesting question, because science advances not just by collecting data, but by learning which witnesses are reliable. Sometimes the universe lies, not maliciously, just thermodynamically. Why this tiny element matters so much. You might be wondering, why do scientists care this much about one trace element? Because lithium is not just lithium here. It is a stress test. If the standard picture of the early universe explains hydrogen, helium, and deuterium beautifully, but stumbles on lithium, then lithium becomes a pressure point for all of cosmology. It forces us to ask, are our stellar models good enough? Are our abundance measurements trustworthy? Are our nuclear reaction rates complete? Did something non-standard happen in the first minutes after the Big Bang? This is why a tiny discrepancy in a tiny amount of an element becomes a giant scientific drama. It is not about batteries. It is not about electric cars. It is not about your cousin claiming Himalayan pink salt can reset your ions. It is about whether the earliest measurable moments of the universe are fully understood. That is not a small question. That is one of the biggest questions humans can ask. The current state of the mystery. So where does the case stand today? Here's the honest answer. The lithium problem is still not cleanly closed. Recent work continues to describe a mismatch between standard primordial predictions and the lithium inferred from old metal-poor stars, often still at the factor of 3 to 4 level. At the same time, modern reviews and models increasingly suggest that stellar depletion and chemical evolution may account for much or even most of the discrepancy, at least in principle. So the field is in an intriguing place. The mystery is real. The classic discrepancy remains widely cited, but the missing lithium may be turning into a story about hidden lithium, processed lithium, or misread lithium, rather than lithium that literally never existed. That is how science often works. A simple contradiction evolves into a layered, maddening, beautiful question. Not who stole the lithium, but which part of our interpretation was too naive? That is a far dangerous mystery, because it implicates us. The cosmic moral. The universe is under no obligation to be easy. It gave us a fireball origin. It gave us stars as fossils. It gave us equations that almost work perfectly. And then, with a tiny wink, it left us a missing element. Or maybe not missing, maybe just misplaced, buried in stellar interiors, scrambled by the first stars, warped by an early universe detail we still haven't caught. That is the genius of the lithium problem. It reminds us that even when our theories are magnificent, reality can still hide a clue in the smallest corner of the table.
somewhere in the oldest stars, in the first minutes of time, or in physics not yet fully understood, the answer is waiting. And until we find it, lithium remains one of the universe's smallest and most elegant acts of defiance. The cosmos made a prediction, the stars gave a different testimony, and now humanity is cross-examining the dawn of time. Drop your theory in the comments. Was it destroyed by stars, hidden by stellar physics, or is lithium the whisper of new physics from the beginning of the universe? And if you want more stories where astronomy, mystery, and reality start looking suspiciously cinematic, subscribe, because the universe is not done confessing.